So far we've drawn our cells and our batteries, and we said, yeah, nice, 10 volts, easy peasy, provided. The bad news is cells in and of themselves. You've got iron baths in them, often lithium batteries, or whatever. And they've still got to conduct that electricity from your iron bath to the exterior of the battery. It doesn't matter how efficient you design your battery. There'll always be a little internal resistance inside. If there's a little internal resistance and it's part of the circuit, i.e. if the battery is connected to a complete circuit, resistor or light bulb or whatever it is, current will flow. And if current flows through here, if current flows through a resistor, then there will be some lost volts. Sad times. All that energy per unit charge we could have spent elsewhere. The difference then, if I erase the rest of my circuit, where's the rubber? There we go. If I strap, instead of a whole circuit, if I just literally put, if I measured the potential difference across the ends of my exterior battery unit, that's the terminal potential difference. That is what we'd normally call the voltage. The terminal potential difference is equal to the EMF minus the lost volts. Okay. So you can think of the EMF. It's not a force, first of all. It's called electromotive force, but again, it's for historical reasons. It's a voltage. And it's the voltage, it's the sort of ideal voltage. If we didn't have those lost volts, we didn't lose any volts, if we didn't have internal resistance, then we'd be okay. Then we'd end up with the EMF as our output. In other words, if you want to measure the EMF, you would you'd do exactly this. You'd put a voltmeter across a battery, and that's it. You would measure the voltage when there's no current flowing. Because voltmeters, okay, they don't literally have infinite resistance, but they have a very high resistance, such that there isn't really any current flowing. If you attach a voltmeter and a voltmeter alone to a cell, you will measure more or less the EMF. If you then connect it up to a circuit and the current starts flowing mostly around the circuit, nice, you will notice that there is a drop here at the voltmeter. That drop represents our lost volts. And it represents the difference between the EMF, our ideal, what we could get, and realistically the output of our battery. The internal resistance of a source is the loss of potential difference per unit current in the source when the current passes through the source. Yeah. So it's that these lost volts are only really activated when current passes through. Okay, hopefully that's clear. If somebody starts talking about electromotive force, for the most part, what they're talking about is the same as if you were talking about voltage. Just that you also need to draw in that little internal resistor for the lost volts. Okay. Sources provide the charge carriers with electrical energy, which is expended in components around the circuit. Yeah, when I talked about voltage earlier, this is more or less the definition. And the picture I kept trying to give you is that electrons rushing around, they get electrical energy, which they then spend on the rest of the circuit. The EMF is then the sort of the currency you're giving these electrons. It's the electrical energy per unit charge. Yeah. If this looks familiar, that's because it is familiar. It's also the definition of voltage. The only difference being these lost volts. Okay. Again, let me tidy up this. Sorry, I'm trying to raise that. Oh, whatever. We can then say, given that if we've got a circuit, we've got our little internal resistor here. So this is the battery itself, the physical battery. We have some sort of circuit that expends all the remaining volts. We can say, look, this the voltage measured as at the entrance and exit to our physical cell is the same as the voltage expended across the rest of the circuit. I.e. it's equal, V is equal to big R multiplied by the current. So we can say the EMF is equal to IR plus I little r. We can then factor out I. And lo and behold, we have the true total of the resistance in the circuit. And this is the circuit resistance. Fab. So the difficulty is that these lost volts are not constant. They depend themselves on the current. So as the current increases in the rest of the circuit, the amount of voltage you're losing also increases. Increasing the current through a source increases the volts lost in the internal resistance and decreases the terminal PD. So you just can't win, really. You know, you can celebrate because you've increased the current, but it's a bit of a Pyrrhic victory because it means you also increase your volts lost. Okay. Slightly bittersweet. Okay. Determine a method of measuring the EMF and internal resistance of a circuit by taking measurements with a voltmeter and an ammeter. Lovely. So it says determine a method. So it's one of these longer experimental planning, but it's only worth 4 marks rather than 6, which is nice. Construct a circuit diagram to show the setup. That's also nice. We like a circuit diagram. Lovely. And your setup would be something like this, which is actually identical to the last one we drew, except we've just included the internal resistance this time. Okay, 2 marks for a circuit diagram. And as I said, it's nice because it has its own conventions. You know exactly how to draw a variable resistor, regular resistor, internal resistor, voltmeter, ammeter, and cell. Okay, so the way we will best measure the internal resistance, yes, technically you can just take 2 measurements, one where there's no current flowing, one where there's some current flowing, but it's best to plot a graph. Adjust current by varying the variable resistance. Plot values for V and I. You've got a voltmeter and ammeter, so why don't you use them? Fixed resistor. The fixed resistor limits the maximum current passing through the cell. Yep, that's true. The ammeter measures the cell current and the voltmeter measures terminal PD. You get a mark just for pointing out what an ammeter and a voltmeter do. And then plot an IV graph and draw a straight line of best fit with the negative gradient. Okay, so because we're measuring voltage outside the cell, obviously we can't sort of get our voltmeter inside the cell to measure EMF directly. What we'll end up measuring is the EMF minus our lost volts. And so if I plot V against I, we've got this mathematical form which looks a bit like Y equals mx plus c. The only difference is it's in a slightly jumbled form. So E is a constant. That's going to be equivalent to C. So our y-intercept will represent our EMF. And the gradient, well, the gradient will be negative, the negative of the internal resistance. M is minus little r. What did the question actually ask for? Oh, to measure the EMF and internal resistance. So we want both. And yeah, just as the text in blue says, the gradient of the graph is equal to minus r, and the intercept of the v-axis, the y-axis, gives epsilon.